Welcome to the course on an introduction to information theory. Today in this lecture we are going to talk about how to quantify information. So we will talk about Shannon's measure of information, and then we will talk about entropy. We will define entropy, conditional entropy, joint entropy, relative entropy, and we will prove some properties of them. We will also talk about what is known as IT inequality. It's an inequality which is used to prove lot of results. We will prove IT inequality, and then we will talk about some properties of entropy such as chain rule, and we will define mutual information. So after this lecture you should be able to quantify information, and you should be able to know what is entropy, conditional entropy, joint entropy, mutual information, and their properties. So Hartley was the first person who was able to quantify information. And how did he quantify information? So Hartley said that, so if you have a random variable x, and let's say there are x takes L different values, then Hartley defined measure of information as log of L. The unit B determines the units of information. If B is 2, we define information in terms of bits. If it is natural log, we define in terms of nats. Now note here, Hartley was able to recognize that to have information, basically a random variable should have multiple possible values. So something which is predictable, something which has known value does not convey any information. So let's consider tossing of coin. So if we are considering a unbiased coin, then with equal probability we will get head and tail, right? So according to Hartley, then the information content here is log of 2. Now there is a problem with Hartley's measure of information, and what is that? To illustrate, let us consider a bag containing two types of balls, black balls and red balls. So let's consider, let's say there are two bags, just call it as bag A and bag B. Each bag, let's say, have 4 balls. So there are 4 balls in each bag. Okay. Now in bag A, let's say 2 of the balls are of blue color and 2 of the balls are of red color. Whereas in bag B, let's say there are 3 balls of red color and 1 ball of blue color. Now according to Hartley's measure of information, in bag A there are 2 possible outcomes. So what I am doing is, I have a bag of these balls and I am picking up a ball and I am showing you the color of the ball, right? So according to Hartley, in bag A there are 2 possibilities. You can either get blue ball or you can get red ball. Similarly, in bag B you have 2 possibilities. You can either get blue ball or you can get red ball. So according to Hartley's measure of information, the information content in both these bags are same, because both have only 2 possibilities. But is the information content same? Look at this. In bag A there is a 50% possibility of getting a blue ball and 50% possibility of getting a red ball, whereas in bag B there is 75% possibility of getting a red ball and 25% possibility of getting a blue ball. So in bag B, if I pick up a ball, it is more likely to be a red ball than a blue ball. So clearly bag B has less information, because the most likely ball that I can guess coming out of bag B is red ball, because there are more red balls than blue balls. Whereas in bag A, blue balls and red balls are equally likely to happen. So clearly the event of picking a ball from bag A has more information, because it's difficult to predict the color of the ball, because blue balls and red balls are equally likely, whereas in bag B, red balls are more likely. So this feature of information was not captured by Hartley's measure of information. So we can see that Hartley missed this crucial piece of information, which is how frequently this event is, basically how frequently these events are happening. So that was taken care of in Shannon's measure of information. So if ith possible value of x, random variable x, has probability pi, then if we weigh the Hartley's measure, which in this case would be log of 1 by pi, if we weigh it by pi and we sum it over all possible values of x, we get what is known as Shannon's measure of information. So you can see here the Hartley's information in some sense is weighted by the probability of occurring of that particular value of x. So let us define what we mean by a support of a function. So if we have a real value function f, then its support is defined as subset of its domain where the function f takes non-zero value, because this probability basically is defined over where pi is greater than 0. So we define a support of a function f as a subset of its domain where f takes non-zero values. So the information content or the uncertainty associated with a random variable, discrete random variable x, can be written as follows. So it is the expected value of minus log of px. So we define this as minus px log px sum over the support set of px. So this is because log of px is defined over those values of px which is greater than 0. So we can define the entropy or the uncertainty associated with a random variable as expected value of minus log of px. Now similarly we can define joint entropy of discrete random variable x and y. So joint entropy of discrete random variable x and y is defined as minus expectation of minus log of joint probability distribution of x and y. So this can be written as minus summation over the support set of joint distribution of pxy log pxy. Okay. Now let us take an example. Let us assume x takes two possible values, x1 and x2, and probability of x1 is p, so the probability of x2 is 1 minus p. So what is the uncertainty or what's the entropy of x? According to definition, it is summation minus probability of x1, that is minus p log p, and minus probability of x2, which is minus log p log of 1 minus p. Now this expression has a special name. It's called binary entropy function. So this is known as binary entropy function, and it is denoted by h of p. In many books they use this small notation, small h of p. I am just avoiding the small notation to avoid confusion with differential entropy, which we will define when we will talk about continuous random variables. So I am denoting this binary entropy function by capital H of p. And if you plot the binary entropy function, it looks like this. So on the x axis you have this probability, and on the y axis I have plotted this binary entropy function. So you can see for p equal to 0, I am close to 0, this is basically here it's 0, and its maximum value is p 0.5, and this corresponds to h of p being 1. Now let us prove an inequality which will be very handy in proving lot of results related to entropy. So let us consider a positive real number r, then we can show that log of r is less than equal to r minus 1 log of e, and this equality happens if and only if r is equal to 1. So if you plot this, to see now log of r is defined for r positive real number. So this would be something like this. At r equal to 1, this log of r is 0, and how will this function look like? It's basically, so it's r minus 1, and the slope here will be log of e. Now note that the graph of natural log of r and r minus 1, they coincide at r equal to 1. I just plotted it, I am just replotting again. So this will be like my log function, and this will be my r minus 1. So they intersect at r equal to 1. And if I consider the slope of this natural log, you can see here this slope here for r less than 1, this slope is greater than 1, and for r greater than 1, this slope is less than 1. So clearly these two graphs will not intersect each other, and as I said, natural log of r is below r minus 1. So this condition holds with equality only if r is equal to 1. If I multiply both sides by log of e, I get this result, which is log of r is less than equal to r minus 1 log of e. This is known as IT inequality. Now let us prove some properties of entropy using this IT inequality. So the first property of a discrete random variable x that takes L possible values is as follows. Entropy is lower bounded by 0 and upper bounded by log of L. The equality on the left hand side happens if and only if p of x is 1 for some particular x, and for all other x it's 0, and equality on the right, which is this h of x equal to log r, this happens if your source is uniformly distributed. So p of x is 1 by L for all x. So let us prove this. So we will first show this result, that entropy is greater than equal to 0. So how do we prove it? Let's write, we know from the definition of entropy, it's minus px log of px summation over all values of x. So let's look at these quantity, minus px log of px over the support set of px. Now clearly when p of x is 1, log of 1 will be 0, so this quantity will be 0, right? And we know that probability lies between 0 and 1. So when p of x lies between 0 and 1, this would be a fraction. So log of a fraction will be minus of some number, and minus minus becomes positive. So since p of x is positive, so minus log of a fraction will be a positive number. So this will be greater than equal to 0. So what we have shown here then is, if for some value of x, p of x is 1, and for other values p of x is 0, then the entropy will be 0, otherwise entropy will be greater than equal to 0. Okay. So entropy will be 0 if and only if px is equal to 1 for every x belongs to the support set of px, but there can be only one such x. For all other values of x, p of x should be 0. Now let us prove the other part, which is hx is less than equal to log of L. So how do we prove this? So we have to show that h of x is less than equal to log of L. In other words, we can show, if we can show that this quantity h of x minus log of L is less than equal to 0, then we would have shown that h of x is greater than h of x is less than equal to log of L. And to prove this result, we are going to make use of IT inequality, which we just proved, that log of r is less than equal to r minus 1 whole multiplied by log of e. So let's look at the proof. So first thing I did was, from definition of entropy, I wrote down the expression for entropy. So this is minus summation over support set of px log of px, and the second term is minus log of L. I write it like this. Now minus log of L can be written as, so I can write this as summation over p of x log of L, because summation of p of x should add up to, so I can write this term like this. So note, I have a common term, and of course x is defined over the support set of px. So if I write log of L in this particular fashion, you can see in this term, this particular term and this particular term is common. So I take this term out. Okay. Now I have minus log of p of x. I have minus log of p of x. That I can write as log of 1 by p of x. So this is how I am writing this, and I have minus log of L, that is this term. Now minus log of L can be written as plus, this can be written as, this term can be written as plus log of 1 plus L, and if I have log A plus log B, that is log AB. So I can combine these two terms and write it like this, log of 1 by L times p of x. Okay, p of x Now this quantity can be simplified using IT inequality. Now what does IT inequality says? IT inequality says that log of r is less than equal to r minus 1 log of e, with equality happening when r is equal to 1. So what is r here? This is my r. This is my r here, right? So I can then write log of r as r minus 1 times log of e. So this can be written as r minus 1 log of e. So then simplifying it, I can write the first term is summation over px 1 by L px, so that's this term, and then the second term is minus summation over supports set of px pxi. So this is less than equal to, this term will be 1 minus 1 log of e, which is basically 0. So then what I have shown here is h of x minus log of L is less than equal to 0. So in other words, h of x is less than equal to log of L. So then if x is a discrete random variable that can take L different values, then the maximum entropy or maximum uncertainty associated with x is equal to log of L, and this happens when r is 1. So when is r 1? So that means 1 by L px is basically going to 1. So p of x should be 1 by L for all x belong to the support set of p. So in other words, px should be uniformly distributed. So when my discrete random variable is uniformly distributed, I will have h of x less than h of x equal to log of L, and that's a maximum uncertainty associated with x. So you can go back and look at our example of tossing of a coin. So when it is an unbiased coin, probability of occurrence of head and tail is same, half. In that case we have the maximum uncertainty, we have the maximum information. Now let us prove some properties of entropy. So entropy computed to the base b can be related to entropy computed to the base a by this particular relation. This is straightforward to prove. We can write log of p to the base b as log of a to the base b multiplied by log of p to the base a. Now what is the definition of entropy? So we have to compute entropy to the base b. So we have to compute minus p log of p, and we have to sum it over the support set of p. Now this, we know that this quantity is equal to this. So we replace this by this in this expression. So we get this expression. Now we are summing over the support set of x. Now please note this quantity log of a to the base b does not depend on x, so I can take this out. So what I get here is minus p log to the base log of p to the base a. So this quantity will be entropy computed to the base a, and this is entropy of x computed to the base b. So I can write then, so this is a relation governing entropy computed to base b and a. Now let us define what do we mean by conditional entropy. So a conditional entropy of a discrete random variable x given an event y equal to some y which has occurred is given by as follows. So the conditional entropy of x given an event y equal to y has happened is given by this expression, which is minus summation over the support set of this conditional probability distribution of x given y, this p of x given by log of p of x given by. So this is basically expectation of minus log of p of x given y equal to y, a particular event has occurred. Now if I have to compute conditional entropy of a discrete random variable x given another discrete random variable y, then this can be computed from this conditional entropy which we just defined now as follows. So conditional entropy of x given y can be given as follows. It is conditional entropy of x given a particular event y has occurred multiplied by the probability of occurrence of that particular event, and we sum it over all y's. So this can be written as expectation of minus conditional distribution of x given y. Now we define what we mean by relative entropy or divergence. So if x and x hat are two discrete random variables with same set of possible values, then the information divergence or relative entropy between px and p of x hat is defined as follows. So you can look at this is expectation with respect to x of log of p of x divided by p of x hat. So let us take a simple example to compute relative entropy. So we have a random variable x that takes L possible values. We have another random variable x hat which is uniformly distributed. So p of x hat is 1 by L for all x belonging to x. Now how do we compute the relative entropy between p of x and p of x hat? That is the expected value of log of px divided by p of x hat. Now what is p of x hat? This is uniformly distributed, so this is basically equal to 1 by L. So if we plug that in here, we get expected value of log of L times p of x. So log of L does not depend on x, so I can take it out. So log of L, and then what I am left with is expected value of log of px. This I can write as minus of expected value of minus of log of p of x. And what is this quantity? This is our entropy. So then I can write down the divergence between p of x and p of x hat is equal to log of L minus h of x for this particular random variable x and x hat. Now divergence between any two probability distribution p and q is always greater than equal to 0. So divergence, so it is in some sense measure of closeness between two distribution. If p is very close to q, the value of divergence will be close to 0, otherwise divergence will be, if p is substantially different from q, divergence will be large. So for qx greater than 0, let us compute minus of divergence of p and q. So I will have to show that this quantity is less than equal to 0. Okay. So from definition of divergence, I know divergence between P and Q is expected value of log of P by Q. So minus of that would be expected value of log of Q by P. So this is minus of divergence between P and Q. Now I will again make use of IT inequality. So this is my, think of this as my R. So I have log of R. Now log of R is less than equal to R minus 1 times log of E. So I will make use of IT inequality. So then this particular term is less than equal to R minus 1 log of E. Okay. Now simplifying, so I will get, this is Px multiplied by Qx by Px, so I will get this term summation over Qx, and here I will get summation over Px. This is less than equal to 1 minus 1, and which is basically 0. So what I have shown is minus of divergence between this two probability distribution P and Q is less than equal to 0, or in other words, divergence between P and Q is greater than equal to 0. Okay. Now we have defined so far entropy, joint entropy, conditional entropy and relative entropy, and we have proved some properties of entropy, like if x is a discrete random variable, we have shown that minimum value of entropy is 0 and maximum value is log of L, where x takes L possible values. Now let us prove some more properties of entropy and define what we mean by mutual information. So joint entropy of random variable x1, x2, x3, xn can be written in terms of their conditional entropy in this particular fashion. For example, if you have h of x1, x2, this can be written as h of x1 plus h of x2 given x1. So we can write this joint entropy in terms of summation of conditional entropy. So how do we prove it? We will write this joint distribution in terms of conditional distribution. Okay. And now we will invoke the definition of joint entropy. What is the definition of joint entropy? It is the expected value of minus log of this joint distribution. And what is this? This is nothing but, this is given by this quantity, product of these conditional probabilities. So if we take log of product terms, what we will get is summation here, and what we will get then is expected value of minus log of these conditional distribution, which is nothing but conditional entropy. Hence we can write this joint entropy in terms of these conditional entropy. This is a very important result. We are going to use chain rule repeatedly to prove different properties of entropy and other things. Now let us define what we mean by mutual information. Mutual information between two random variables x and y. So mutual information between two random variables x and y is defined as divergence between the joint distribution and these marginals. So it is defined as the expected value of log of joint distribution of x and y divided by marginal distribution p of x and p of y. So this is the definition. This is how mutual information is defined. Now this we can write as, so we can write this joint distribution in terms of conditional distribution. We can write this as probability of x given y into probability of y. So then this term, this particular term can be written like this. Okay. Now log of a by b, this can be written as log of a minus log of b. So then we can write this as, so summation p of pxy log of 1 by px, that is this term, and then summation over pxy log of x given y, that's this term. Okay. Now what is this term? Summation, now does this term depends on y? No. So if we sum it over y, what will we get? We will get p of x. So that's what we will get. So the summation over xy, if we sum over y, this does not depend on y. So if I sum it over y, what I will get is p of x. So this particular term that I have here can be simplified to this, and plus this term can be written as minus of this term. Now what is this? This is nothing but our entropy of x. And what is this term? This is the conditional entropy of x given y. So what is mutual information this? This is the uncertainty associated with source x. This is the uncertainty in source x given y. Then what is the difference telling me? So this is telling me the information that y is conveying about x. Now why is this mutual term coming here? We will show that this mutual information can also be written as uncertainty in y minus uncertainty of y given x. So whatever information y is giving about x, the same information is also provided by x about y. So let's do that. So we have just shown that mutual information can be written like this. Now we know that we can write this joint entropy using chain rule. We can write it in this particular fashion. This is h of x plus h of y given x. Now I again apply chain rule in a different fashion. So I can write this joint entropy as h of y plus h of x given y. So if I compare these two equations, what I get is as follows: h of x minus h of x given y is same as h of y minus h of y given x. And what is this? This is nothing but mutual information between x and y, and this term is mutual information between y and x. So you can see whatever information y is giving about x, the same information is conveyed by x about y. So this is our mutual information. Now let us prove some more properties of entropy function. So if you have two discrete random variable x and y, then conditioning cannot increase entropy. So entropy of x given y is always less than equal to entropy of x, and this equality happens only if x and y are independent. In that case, y does not provide any information or reduction in uncertainty of x. So how do we prove this result? There are a number of ways you can prove it. Now mutual information can be written like this: it's uncertainty in x minus uncertainty in x given y. Now we also know that mutual information is nothing but its relative entropy or divergence between this joint distribution of x and y and product of these marginals p of x and p of y. And we have shown that divergence is all between two distributions p and q is always greater than equal to 0. So using those results, then we can say that mutual information, because mutual information is divergence between these two distributions, so mutual information is also greater than equal to 0. Now we plug that in here, we have proved that h of x is greater than equal to h of x given y. Now similar to the chain rule for entropy, we can also define chain rule for mutual information. So mutual information between x1, x2, x3, xn and y can be written in terms of conditional mutual information of xi and y given x1, x2, xi minus 1. So proof follows like this. So first we write the definition of mutual information in terms of entropy and conditional entropy. So this mutual information between x1, x2, xn and y can be written as joint entropy of H minus joint entropy of this x1, x2, xn given y. Now each of these quantity can be written in terms of conditional entropy using chain rule. So this joint entropy of x1, x2, x3, xn can be written like this. Similarly, this joint entropy given y can also be written in terms of using chain rule in terms of its conditional entropy. So if we combine this, we can see that this is nothing but mutual information between xi and y given x1, x2, x3, xi minus 1. We can also similarly show chain rule for divergence. So if you have divergence between joint distribution of x and y, p of x of y and q of xy, this can be written as divergence between px and qx plus divergence of conditional distribution of y given x and q of y given x. Again, the proof is straightforward. What we do first is, from definition of divergence, we write the expression for divergence between these two probability distribution p of xy and q of xy. So this follows from definition. So from definition we get this. Now these joint distributions can be written in terms of conditional distribution. So I can write this like this, and similarly I can write this in this particular fashion. Now I will separate these two terms. So I can write this particular term I can write this as p of x q of x multiplied by p of y given x and q of y given x, and there is a log here. So it is log of a into b. So this will be log of a plus log of b. So then this is my log of a term and this is my log of b term. Now again, this particular quantity does not depend on y. So when I sum it over y, I am essentially summing up this over y. So if I do that, what I will get is p of x. So this is summation over x, p of x log of p of x by q of x, which is nothing but divergence between p of x and q of x. And similarly, this particular term can be written as divergence between the conditional distribution of y of p y given x of p and q y given x. So this is the chain rule for entropy function. Now we'll just conclude with one example to illustrate how to compute mutual information. So you have a single unbiased dice which is tossed. So this is a dice, so this has numbers from 1 to 6 and you're tossing this coin. Now if the face of the dice is 1, 2, 3 or 4, what you are doing is you are tossing a unbiased coin. What is an unbiased coin? An unbiased coin is a coin which has head and tail. Okay, so if the outcome of the dice is 1, 2, 3 or 4, I am tossing a coin, and if the outcome of the dice is 5 or 6, then I am tossing the coin twice. And this is the fair coin which I am tossing, unbiased coin. Now I want to find out what is the information about the face of the dice that is conveyed by number of heads obtained. So again, what I am doing is I am first rolling a dice, and depending on what the number is, I am tossing a coin. So you can think of it basically, so input x is the outcome of the dice. So there are two possible outcomes, x1 and x2. So if the dice outcome is 1, 2, 3 and 4, that's one possible outcome, and if the dice outcome is 5 or 6, that's one possible this thing. Now what I do is, if I get 1, 2 or 3, I toss a coin once. So if I toss a coin once, what can I get? I can get a case when there is no head. If I am tossing a coin once, I can get a condition when there is no head, or I can get a condition that there is only one head. Correct? Now what am I doing when I am getting 5 or 6? I am tossing the coin twice. So what are the possible outcomes as far as head is concerned? I can get no head. In none of those two tries I got an head, or I can get one head, or I can get two heads. Okay. Now since this dice is a fair dice and this coin is also fair dice, then this will happen with probability 2 by 3 and this will happen with probability 1 by 3. So given that I get x1, probability of getting y0, which is no head, is half, because my coin is a fair coin, and this probability of getting one head is also half. Now if I get x2, which is the face of the dice is 5 or 6, then I am tossing the coin twice. So what's the probability of getting no head? That is half into half. So this will be 1 by 4. And what's the probability of getting two heads? So I have to get head in the first toss as well as head in the second toss. So that probability is half into half. So that's again 4. And what's the probability of getting one head? I can either get head in first toss and tail in the second toss, or I can get tail in the first toss and head in the second toss. So probability of this and probability of this, they add up to half. Okay. So that's what I have written here. So x is a random variable that denotes the outcome of the throwing of the dice. So this can be either 1, 2, 3, 4. I have one set of actions I am taking based on whether the outcome is 1, 2, 3, 4, and I have other set of actions which I am taking depending on whether the outcome is 5 or 6. And let y is the output of my tossing of the coin, which basically I am interested in counting number of heads. Now as I said, there are two possible actions I am taking based on what I get as a result of throwing of the dice. So I am calling x1 if I get face of the dice as 1, 2, 3, 4, and x2 if I get face of the dice as 5 or 6. Similarly, my outcomes I am writing it as y0, y1, y2, denoting no head, 1 head, and 2 head. I have already mentioned, because probability of getting x1, which is probability of getting face of 1, 2, 3, 4, that probability is 2 by 3 because it is a fair dice, and probability of getting 5 or 6 is 1 by 3. Similarly, if I get x1, which is dice value, face value of 1, 2, 3, 4, I am tossing the coin once. So in that case, probability of getting no head is same as probability of getting 1 head, which is half, and I can never get 2 heads because I am tossing the coin only once. Similarly, if I am getting 5 or 6, I am tossing the coin twice. So probability of getting no head or probability of getting 2 heads is 1 by 4, this we have just shown, and probability of getting 1 head is half. Okay. So now that we know what is the probability of getting x1, what is the probability of getting yi given xi, we can find out what is the probability of getting y0, y1 and y2. What is the probability of getting y2? That is the probability of getting x1 into probability of y0 given x1 and plus probability of y0 given x2 into probability of x2. Similarly, we can compute these probability of p of y1 and p of y2. In this particular example, this turns out to be p of y0 turns out to be 5 by 12, p of y1 comes out to be half, and p of y2 comes out to be 1 by 12. So then uncertainty in y can be given as minus 5 by 12 log of 5 by 12 minus half log of half minus 1 by 12 log of 1 by 12, and that comes out to be 1.325 bits. Similarly, we can compute conditional entropy of y given x. This is given as conditional entropy of y given x1 into probability of x1 plus conditional entropy of y given x2 multiplied by probability of x2. So in the similar fashion, we can find out what is entropy of y given x1. This is basically minus half log of half, and uncertainty in y given x2 is minus 1 by 4 log of 1 by 4 plus minus half log of half and minus 1 by 4 log of 1 by 4. This is just following the definition of entropy. So if we do that, this term comes out to be 1 and this term comes out to be 3 by 2. So computing this, we find out that uncertainty in y given x is given by 1.167. So then the mutual information between x and y or y of x is basically given by uncertainty in y minus uncertainty in y given x, and this is comes out to be 0.158 bits. So this is an example to illustrate how we can compute mutual information. So with this we conclude this lecture. Thank you.